Welcome students once again, and in the previous video we have stated and proved Cauchy's first theorem on limits, and now we are moving on to the Cauchy's second theorem on limits, its converse as well as Cicero's theorem. So let us see what is the statement of Cauchy's second theorem on limits. Cauchy's second theorem on limits. So first we will see what it states. It says that let an be a sequence of positive terms. It is a sequence of positive terms an if limit an plus 1 over an as n approaches infinity exists. Exist means it may be finite, it may be infinite. It may be finite, it may be infinite. That means this sequence an plus 1 upon an, it may converge, it may diverge. In both the cases, if this limit exists, then limit of an raised to the power 1 by n as n approaches infinity also exists, and not only exists, but this limit an raised to the power 1 by n as n approaches infinity, it equals limit n approaches infinity an plus 1 upon an. So this is the statement of Cauchy's second theorem on limits. If this limit exists, finite or infinite, then this limit also exists, and not only it exists, but it is equal to the previous one. The converse is not true. That means if this limit exists, then it is not necessary that this limit also exists. Equality is the secondary case. Even if this limit exists, it is not necessary that this limit exists. This is the converse. That means the converse of this theorem is not true. So let us see how to prove the direct part, the Cauchy's second theorem on limits, where we are given that limit n approaches infinity, an plus 1 upon an exists. So let this limit exists and equal to L. Say here in this part I am taking this L to be a finite number. I am not taking the case of infinite, that I will cover into the second part. So here let it be case 1 where this is L, it is finite. If L is if L is infinite, then we will handle the case in the second part, in case 2. So here I am taking this limit exists and is equal to L. By the definition of this limit, or you can say that this sequence an plus 1 upon an, it converges to L. By the definition of convergence, or by the definition of limit, for given epsilon greater than 0, however small, there exists natural number m definitely belonging to n such that mod of an plus 1 upon an minus L is less than epsilon for every n greater than or equal to m. This is true for every n greater than or equal to m. So I'll try to simplify this inequality. For that, I'm going to write this, that this inequality can also be written as minus epsilon is less than an plus 1 upon an minus L less than epsilon for every n greater than or equal to m. Because if mod x is less than a, this clearly means that minus a is less than x is less than a. This is from your basic knowledge of inequalities. So I have used this, I have written this inequality in this form, and now add L to each part of this inequality. Adding L, you will get L minus epsilon here. This minus L will be removed as we have added L, and on the right hand side this epsilon you will get L plus epsilon. because we have added n to all the parts of this inequality. Now this is true for every n greater than or equal to m. That means this is true for n is equal to m plus 1, this is true for n is equal to m plus 2, this is true for n is equal to m plus 3, and so on. So take, or you can say replace n by m plus 1, m plus 2, m plus 3, and so on, n minus 1. Here in this inequality, what you are going to get, if you will replace your n by m plus 1, start with m, replace from m, start from m to n minus 1. If we will put n here, m here, this will become L minus epsilon less than a m plus 1 upon am less than L plus epsilon. Because we have taken m, so definitely n is greater than or equal to m, so you can take n is equal to m. Now taking n is equal to m plus 1, what this inequality will become? L minus epsilon less than, here you are substituting m plus 1 in place of n. So you will get a m plus 2 over a m plus 1 less than L plus epsilon. Similarly, you will get L minus epsilon less than a m plus 3 divided by a m plus 2 less than L plus epsilon, and so on and so on. In the last, we are replacing n by n minus 1. So replacing n by n minus 1 here, what you will get? You will get L minus epsilon is less than, this n will be replaced by n minus 1, so you will get n minus 1 plus 1. Minus 1 and plus 1 will be cancelled. You will get a n divided by a n minus 1 less than L plus epsilon. So you are having here some inequalities. How many inequalities these are? You have started from m and you have ended to n minus 1. So total number of these inequalities is n minus m. Multiplying all these n minus m inequalities, what you are going to get? See, multiplying all these n minus m inequalities, on the left hand side of each of these inequalities, you are having L minus epsilon. So L minus epsilon into L minus epsilon into L minus epsilon into L minus epsilon, how many times? N minus m times. So you will get L minus epsilon raised to the power n minus m. Now, in the center, what you are going to get? This is am in the denominator, this is this is am plus 1 in the numerator, this is am plus 1 in the denominator, will be cancelled out. So these two terms will be cancelled out when you will multiply all these inequalities. Similarly, this am plus 2 is in the numerator and this am plus 2 is in the denominator, so will be cancelled out. Similarly, all these terms will be cancelled and you will be left with an in the numerator and am in the denominator. So this product will become an upon am is less than. On the right hand side, once again you are having the same term, L plus epsilon, L plus epsilon, L plus epsilon, L plus epsilon. How many times? N minus m times. So it will become L plus epsilon raised to the power n minus m. So now I'm going to rub this part because no more this part will be required now in the proof. Now this am, this is a positive number because our sequence, we have started with let a and b a sequence of positive terms. So am is also positive. So multiply this inequality throughout by am. So what you will get? You will get am here. This am will be removed from here because you are multiplying by am, and here you will get am. So we have multiplied the inequality throughout by am. And now raise all the terms to the power 1 by n. That means what you have to do? This term raised to the power 1 by n, this raised to the power 1 by n, this raised to the power 1 by n. So what you are going to get now? This is am raised to the power 1 by n, L minus epsilon raised to the power n minus m over n. So that means you can say 1 minus m upon n less than in the center you will get an raised to the power 1 by n is less than, on the right hand side once again you will get am raised to the power 1 by n and L plus epsilon raised to the power n minus m over n once again is 1 minus m upon n. So this inequality, suppose it is A. I'm numbering this inequality as A. Now look at the first part, this one, am raised to the power 1 upon n, L minus epsilon raised to the power 1 minus m upon n. So what will be its value if you take limit n approaches infinity? Now L approaches infinity, this 1 upon n will become approaching towards 0. Something positive raised to the power something that is approaching towards 0 is equal to 1. So this term is 1. Here this m upon n will become 0 because n is approaching towards infinity. So 1 minus 0 is 1. L minus epsilon raised to the power 1. So this limit becomes equal to L minus epsilon. Similarly, for this right hand side term, you will get limit n approaches infinity, am raised to the power 1 by n, L plus epsilon raised to the power 1 minus m by n is equal to, on the same lines, this is 1 upon something approaches infinity, so it is 0. Something positive raised to the power 0 is 1. Here, this is 1 minus, once again it is 0, so 1 minus 0 is 1, so it is equal to L plus epsilon. Or you can say that this sequence is converging to L minus epsilon and this sequence is converging to L plus epsilon. Once again, applying, either you can say the definition of limits or you can say the definition of convergence of sequences. What you are going to get from the first, this part, for given epsilon greater than 0, there exists m1, you can say, there exists m1 natural number such that this is your, suppose this part is your, say xn. So xn approaches something. So xn minus this mod is less than epsilon for every n greater than or equal to m. So you can write such that mod of this term am raised to the power 1 by n, L minus epsilon raised to the power 1 minus m by n minus the limit. The limit is L minus epsilon. So minus the limit L minus epsilon mod is less than epsilon for every n greater than or equal to m1. And for the second one, on the same lines, for given epsilon greater than 0, you can say there exists m2 belonging to n such that the similar expression you will get am raised to the power 1 by n, L plus epsilon raised to the power 1 minus m by n minus L plus epsilon mod is less than epsilon for every n greater than or equal to m2. This part is true for every n greater than or equal to m. This part is true for every n greater than or equal to m1. And this inequality is true for every n greater than or equal to m2. So you are having three natural numbers, fixed natural numbers, m, m1 and m2. Whenever your n is greater than m, this is true. Whenever your n is greater than or equal to m1, this is true. And whenever your n is greater than or equal to m2, this is true. So you choose maximum of these m, m1 and m2. Say it be m3. So if your n is greater than m3, definitely n will be greater than or equal to m, n will be greater than or equal to m1 and n will be greater than or equal to m2. So all these three inequalities will be satisfied. So what you are to do, take m3 to be maximum of m, m1 and m2. That means for every n, whenever your n is greater than or equal to m3, definitely n will be greater than or equal to m. And if n is greater than or equal to m, this will be satisfied. If your n is greater than or equal to m3, definitely it will be greater than or equal to m1. and if your n is greater than or equal to m1, this will be satisfied, and whenever your n is greater than or equal to m3, n will be automatically greater than or equal to m2, so this inequality will automatically be satisfied. Let me simplify these three. So I'm writing here, this is true for every n greater than or equal to m3. This is also true for n is greater than or equal to m3. This is also true for n is greater than or equal to m3, because we have taken m3 to be maximum of these three, m, m1 and m2. Now let me solve these inequalities. Once again, this is mod of something less than a. If mod x is less than a, that means minus a is less than x is less than a. So if you want to remove this mod, what you will get? Minus epsilon is less than this, is less than that. In the same lines, you can solve this. So if you want to remove this mod, what you are going to get? You will get minus epsilon here. And now, add L minus epsilon to all terms of the first inequality and L plus epsilon to all the terms of the second inequality. So when you will add L minus epsilon to all these inequalities, here you will get L minus epsilon. So that means L minus 2 epsilon. L minus 2 epsilon. Here this minus L minus epsilon will be removed. And on the right side, you will get is less than L, because minus L minus epsilon, and you are already having plus epsilon, so this will be cancelled, you will be left with L. Similarly, when you will add L plus epsilon to all these terms, so adding L plus epsilon here, L plus epsilon minus epsilon, so minus epsilon and plus epsilon will be cancelled, so you will get L here. This minus L plus epsilon will be removed as you are adding L plus epsilon to all the terms, and the right hand side will become L plus 2 epsilon. Now let me name this as B and this as C. Now I'm going to combine these three, but how to combine, this is an important step. I'm starting from here, and where I will end will be in the subsequent terms. So I'm starting from here, L minus epsilon, L minus 2 epsilon, or if you say your epsilon is equal to epsilon dash by 2, then this 2 epsilon will become epsilon dash. So you can say L minus epsilon dash is less than this term I have written here, is less than this one. So I am taking only this part of the first inequality. So it is a m power 1 by n, L minus epsilon 1 minus m by n. I am just considering this part of the inequality B. And now I am moving on to inequality A. This term is here. am 1 by n, L minus epsilon raised to the power 1 minus m by n, and this is less than an power 1 by n. Further, this an power 1 by n is less than am power 1 by n, L plus epsilon raised to the power 1 minus m by n. And now I am shifting on to the inequality C, and I am starting from here now. This portion, this term is same as this term, and this is less than L plus 2 epsilon, or you can say L plus epsilon dash. So this is less than L plus epsilon dash for every n greater than or equal to m3. Now this is less than this is less than this, and you know that less than is a relationship which is transitive. If A is less than B and B is less than C, then definitely A is less than C. So what you are going to get, that L minus epsilon dash is less than this term, and then I'm shifting on to this term, is less than a n raised to the power n, and this is less than L plus epsilon dash. So this is less than L plus epsilon dash for every n greater than or equal to m3. And now I'm going to write this inequality in other form. In other form, that means in the modulus form. So how can I write this inequality in modulus form? For that, add minus L to all the parts. adding minus L here, this L and minus L will be cancelled. You will be left with minus epsilon dash. Minus epsilon dash is less than, this is your a n raised to the power 1 by n, and I have added minus L. And in the last part, L plus epsilon dash, and adding minus L to this, L and minus L will be cancelled. You will be left with epsilon dash for every n greater than or equal to m3. And now clearly you can see that this can be written in the modulus form as a n power 1 by n minus L mod is less than epsilon dash for every n greater than or equal to m3. That means for epsilon dash greater than 0, however small, you always have a natural number m3 such that a n power 1 by n minus L is mod is less than epsilon dash for every n greater than or equal to m3. And that means, or either you can say by the definition of limit, or you can say by the definition of convergence of sequence, you have limit of this a n raised to the power 1 by n as n approaches infinity is equal to this L. And in the starting, we have started with L is equal to limit of a n plus 1 upon a n as n approaches infinity. So that means limit of a n raised to the power 1 by n as n approaches infinity is same as limit of a n plus 1 upon a n as n approaches infinity. And that is the first case where we have taken L to be a finite number. If this limit exists, this limit also exists and is equal to this limit. So in the first part we have concluded that the Cauchy's second theorem on limits is true. Now let us move on to the second case. Second case means when the limit L is not a finite number but it is infinity. So if it is infinity, how we have to proceed? So case 2, if limit n approaches infinity, a n plus 1 upon a n is L is equal to infinity. If limit of this is infinity, then what will be the limit of its reciprocal? Will definitely be 0. So this means limit of a n upon a n plus 1 as n approaches infinity is equal to 0, and 0 is finite. This can also be written as, you can write it as limit n approaches infinity 1 upon a n plus 1 over 1 upon a n is equal to 0. And take this 1 upon a n as bn. Take this as bn. So that means limit n approaches infinity, bn plus 1 upon bn is 0. Now bn, an was a positive term sequence, so bn plus 1 its reciprocal is also positive. So you are having a sequence of positive terms bn now, such that limit n approaches infinity, bn plus 1 upon bn is 0. By case 1, here the limit is finite. By case 1, we can say that by using case 1 that we just have proved, by using case 1 we have limit bn raised to the power 1 by n is same as limit bn plus 1 upon bn as n approaches infinity. Here also n approaches infinity. And now substitute the value of bn to be equal to 1 by an. So what you will get? You will get 1 upon an here. And when you will substitute bn is equal to 1 upon an here, you will get once again an upon an plus 1. This 1 upon an raised to the power 1 by n can also be written as 1 upon an raised to the power 1 by n. And once again reciprocate both sides. Reciprocating both sides, on the left hand side you will get limit n approaches infinity, an raised to the power 1 by n is the same as limit n approaches infinity, and the reciprocal of the other side will be an plus 1 upon an. That means in the second case, Cauchy's second theorem also holds well. So this is the complete proof of Cauchy's second theorem on limits. In the next video, we will discuss its converse as well as Cicero's theorem, and if time allows, we will move on to Cauchy's Stone's theorem as well. Till then, thank you once again.